Okay, this section we're going to be looking at the history of acids and bases and how the theory has changed over time, and how we sort of have moved from our junior understanding of acids and bases such as H plus and OH minus to more sophisticated understandings of acids and base theory. So let's check out what's in the syllabus and go from there. Alright, so here is the syllabus statement here where it says explore the changes in definitions and models of an acid and base over time to explain the limitations of each model, including but not limited to. Don't you love those statements? So it explicitly says the Arrhenius theory and the Brouwer-Lonsted theory. However, we're going to be looking at some others because these other sort of theories are classically described in a lot of chemistry textbooks and have previously been described in the previous old chemistry syllabus and crop up their heads from time to time. So we're going to cover all of these. So we're going to start off with Lavoisier, right? Antoine Lavoisier. Then we're going to move into Davy. That's what this first video is going to be looking at, right? Humphrey Davy and Antoine Lavoisier. But then as we move along in the next series of videos, we're going to be looking at the Arrhenius theory and the Brouwer-Lonsted and sort of go on from that into how we can describe acids and bases and salts, etc. So let's get into it. Okay, well, if we go back to around about 1776, in the 17th century, well, that's actually the 18th century, isn't it? But we've got this date here. Now, these dates are not, you're not expected to memorize these dates, but you are expected to memorize the order in which these different theories have occurred. And so here we have Antoine Lavoisier, and how I've written his name here is I've tried to give you a visual connection between his name and his main idea. So you can see here in his name I've highlighted the O and made it big. Why? Well, because Antoine Lavoisier basically believed that materials that had oxygen in them were acidic. And how did he come to that conclusion? Well, we know the periodic table here is broken up into metals and non-metals. And so what he did, he studied non-metal oxides. So all these oxides over here. So you have carbon, nitrogen, fluorine, chlorine. When he looked at the oxides of those, he found that they were acidic. So for example, carbon was carbon dioxide, and he put carbon dioxide in water, gave you carbonic acid. When he did for sulfur dioxide and sulfur trioxide gases through water, they produced sulfurous acid and sulfuric acid. When he did nitrogen dioxide, he found that he had nitrous acid and then nitric acid. So by studying these non-metal oxides, he found that they had acidic properties, and so therefore he said that acids must contain oxygen, and so that's why I've got a capital O there for his name, to try and link oxygen to Lavoisier's theory. But what's the problem with this? Well, this theory did not explain why metal oxides such as sodium oxide and magnesium oxide were not, oops, look at that, bit of a typo, were not acidic. In fact, if you put sodium oxide into water, it's basic. So how does that work? So according to Lavoisier's theory that acids contain oxygen, didn't really work to explain where we had metal oxides producing basic solutions. Remember back in year 11 when you looked at the trends across the periodic table, and the metals on the left hand side, the metal oxides gave you basic, then you have some metals in the middle, aluminium oxide, etc., which were amphoteric. Remember, they had the ability to react as an acid or a base. And then as we move to the right hand side, the non-metal oxides such as carbon, nitrogen, sulfur, etc., they gave you acidic oxides. So we now know these properties change across the periodic table, and we can explain that with our current theory of acids and bases, but Lavoisier could not explain why sodium and magnesium oxide gave basic solutions, even though he had turned around and said, well, sulfur trioxide, etc., the non-metal oxides gave acidic solutions. Right? Other chemists that were around at the time, Joseph Priestley, for example, formed hydrochloric acid, and he showed that hydrochloric acid produced an acidic solution. So this also went in the face of Lavoisier's theory that acids contain oxygen. Well, hydrogen chloride contains no oxygen, yet it was acidic. So there was a problem, there were some limitations. So let's see how we moved on from that. The next person to sort of put forward a major theory that was around was Humphrey Davy. Now with him, what you can do here, and I didn't do it with his name, but with his first name, I'm going to change that to red or pink or something like that, and we can just highlight the H, because Humphrey Davy was all about hydrogen, acids containing hydrogen. Okay, and so around about 1810, he basically said that acids were substances that contained a replaceable hydrogen. Okay, now what does that mean? Well, let's have a look. Here we have some zinc, and we have some hydrochloric acid, some HCl. Remember, Joseph Priestley previously was investigating this anyway, but Davy said that if this solution here, right now I've used hydrochloric acid, you could use other materials like such as H2SO4 or whatever it might be, that this material here, if the metal replaced the hydrogen from solution and gave you hydrogen gas, then this material here was acidic. Of course, we know these now are single replacement reactions or single displacement reactions, but this was Humphrey Davy's investigation into acids, and he said that acids were substances that contain a replaceable hydrogen, and so he had HCl was in there. However, that was a problem because it could not explain why other substances that contain hydrogen were not acidic. For example, ammonia. Ammonia has hydrogen. Why isn't that acidic? Ethanol, for example, also has hydrogen. Why is that not acidic? So even though Humphrey Davy's definition can be used for hydrochloric acid, sulfuric acid, carbonic acid, phosphoric acid, hydrofluoric acid, all those sort of ones, they do have hydrogen in it, but it can't explain why some substances that have hydrogen are not acidic. To learn more about this next movement, we've got to, of course, get to the next video where we look at the next person in our series. So I'll see you then. Right, before we go to the next video, I want you to check out more courses that we have here on our YouTube channel, which are just small snippets from the actual bigger courses that we have on theflipteacher.com. Of course, with all of our courses, we try to incorporate practical sessions. We have study cards, we have posters that you can print off and stick around your room and do a lot more. We have up to 68 or more videos per course. That's like 9 to 10 hours of material that really delve deep into the syllabus and looking at essential content, skills, mathematical manipulations, and a lot more. So if you like that, go over to theflipteacher.com and check it all out, and I'll see you in the videos.